Hello, and thanks for your continued interest in the subject of shaft alignment. This tutorial on preliminary alignment checks and corrective measures will discuss information that will hopefully assist anyone who is responsible for installing or maintaining rotating machinery, for people who evaluate the operational or mechanical performance of machinery, and for technicians and engineers who are responsible for rotating equipment. So, this information is intended for trades personnel, maintenance supervisors, training instructors, mechanical procedure writers, vibration analysts, engineers, maintenance managers, and any interested operations personnel. The major topics in this tutorial will discuss the basic roughing in techniques for your initial alignment of machinery. You will be introduced to the 5 primary alignment measurement methods. We will also cover how to override a runout condition when taking your measurements. When you first set rotating machinery onto the base, there can be a considerable amount of misalignment. At this point, there is a good chance that the shafts are so far out of alignment that the high precision measurement tools need to be put aside until we get the shafts a little bit better aligned by using your eyesight or straight edges or feeler and taper gauges. All you're trying to do here is get the shafts close enough so when we take measurements with more accurate devices, we stay within the operating range of these sensors. There are currently 5 precision alignment measurement methods practiced in industry. The reverse indicator method, which is also called the reverse radial or double dial method, the face and rim method or face peripheral method, the double radial method, the shaft to coupling spool method, and the face-face method. It is important to understand that there is no one alignment method or one alignment tool that can effectively measure the amount of misalignment on every drive system in existence. There are advantages and disadvantages to each of these methods. A true alignment specialist knows how to perform all of these methods, understands their limitations, and selects the best method for their particular alignment situation. In some cases, it is possible that more than one method would work in certain circumstances. In other cases, you might have but one good choice to select from. It is also important to understand that every alignment measurement tool somehow, some way, is using one of these methods to measure the center lines of rotation of 2 shafts. Here, for example, mechanical dial indicators are shown as the measurement sensor, but other types of sensors could be used, such as linear encoders, linear variable differential transformers, a light beam traversing across a photodiode or across a charge couple device, or proximity probes to take the measurements. In fact, there is really neat systems that use vernier calipers that were invented in the 18th century that very few people know about. Mechanical dial indicators will be used as the primary measuring device when teaching these methods. Dial indicators are relatively inexpensive, readily available everywhere, and accurate to 1 mil, which matches the thinnest shim stock you can buy. They're needed to measure runout, are used for softwood lift checks, can be used to monitor lateral movement of machinery, and don't require batteries. For those of you who have not performed all of these methods, or maybe any of these methods, the key is to learn them one at a time. There are training tutorials dedicated to each one of these methods. If you have the desire and ambition, it's not a matter of if you will learn them, just a matter of when. Oh, one more thing. All of these methods can also be performed on shafts that are in vertical positions, or any position for that matter. Some of you might, for example, have vertical pumps. Many people assume that vertical pumps that are driven by motors don't need to be aligned because everything has been machined to fit perfectly. Really? Is that a fact? If you ever have to work on vertical pumps, I strongly suggest that you check the alignment. You might be surprised at what you find, which is why there is a training tutorial on alignment of vertically oriented shafts. For any of the methods, a bracket will be attached to at least one shaft, a span bar will be used to reach across the coupling, and a dial indicator placed on the other shaft. The dial indicator is placed in the 12 o'clock or top position as the normal starting position. The stem of the indicator is plunged in about halfway in its total travel, and the number dial is set so the needle is pointing at 0. You should then get a sheet of paper and a pencil to record your measurements and note which shaft the dial indicator was taken readings on. Here, in this particular photograph, the bracket is attached to a pump shaft and the dial indicator is taking measurements on a motor shaft. So I would probably call these the pump to motor readings or just the motor readings. This is somewhat important because you can easily become confused later on if you were doing the reverse indicator method, where you took readings on both the motor and the pump and you forgot which readings went with what shaft. The next step is to rotate the shaft, bracket, and dial indicator through a 90-degree arc so the indicator is now on one side of the shaft. That seems simple enough, but we need to talk about a few items here. Before you rotate the shafts, make sure there is some lubricant in the bearings, particularly if your shafts are supported in journal bearings. As far as shaft alignment is concerned, it does not matter which way you rotate the shafts. It is suggested that you rotate in the normal direction of rotation, but you could rotate backwards as long as you don't damage the bearings, which should have some lubricant in them right now if I forgot to mention that. The shafts of small rotating machinery, like the one shown in the photograph, can usually be rotated by hand, and you should not use the alignment bracket to rotate the shaft. For medium to large machinery, it is suggested that you use a strap wrench to rotate the shafts. Yes, I know, nylon strap wrenches have a tendency to slip. Get a 6-inch piece of 180 grit emery cloth, fold it over twice, and place it in between the strap wrench and the shaft for some added friction. Please refrain from using a pipe wrench to rotate the shafts. I know you have some big ones in the plant someplace, but find something else. You can use a chain wrench, but place a piece of hard rubber or copper sheet metal or something where the teeth of the chain wrench are to prevent from damaging the shaft. We're supposed to be aligning the machines, not putting gouges in the shaft. As you begin to rotate the shaft, bracket, and indicator through a 90-degree arc, watch what happens to the dial indicator when rotation starts. Is the needle rotating in a clockwise or a counterclockwise direction? Remember, when the stem of a dial indicator is getting pushed in, the needle rotates in a clockwise direction, and the convention for that is a positive reading. If the stem of the dial indicator is moving outward, the needle will rotate in a counterclockwise direction, and the convention for that is a negative reading. You shouldn't be in a rush here, so rotate slowly so you can observe what is happening. Frequently, I am working with someone during this process. If it is my job to be the person watching the indicator, as a courtesy, I will verbally call out what position the indicator needle is at so they know what's going on too. If it's my job to rotate the shaft, and I see that the person who is supposed to be watching the indicator is distracted or apparently confused, I stop and ask, "Where are we at?" If I hear, "The needle is pointing at 40, I'll ask, "Is that a plus 40 or a minus 60? And I wait until that person looks me in the eyes. If there's any hint that the person is not sure, my response is, "Okay, no problem. I'm going back up to the top and start over again so we know exactly what the reading is, because everything we do from here on out is directly related to the accuracy of the measurements we get. If we get bad measurements, we're going to get bad results, and I don't want to do this twice if I can help it." So now, you've made your first 90-degree rotation. You've carefully watched the dial indicator through the quarter turn, and you're on the side. Now, again, this might seem like a minor point, but what side are you on? I don't know about anybody else, but I use compass directions for my side readings, like north, south, east, and west. The reason I do this is that when I go to correct a sideways misalignment condition, I will tell myself that I need to move the inboard end of the motor 40 mils to the north and the outboard end of the motor 20 mils to the south. This seems to make things less confusing than move the inboard end of the motor 40 mils to the left, because I may have been looking at the machine from one side and the person who may be moving the machine is looking at it from the other side. There is nothing more embarrassing than moving a machine the right amount the wrong way. So you can use compass directions, or left and right, or port and starboard, or riverside and hillside, but be consistent. Before you make your next 90-degree turn, it might be a good idea to write down your side reading on your recording sheet. This particular measurement is probably the most problematic one for a lot of people. Since the dial indicator will eventually be in an upside down position and difficult to see even laying on the floor, a small mirror comes in handy to watch the indicator as you make this 90-degree rotation. To add to the frustration, when you watch an object in a mirror, the motion is in reverse. So if a needle is rotating clockwise, in a mirror, it appears to rotate counterclockwise. So even for people who are adept at reading a dial indicator, it is suggested that before you start the next 90-degree rotation to the bottom, begin by verifying what the indicator reading was on the side, and then rotate the shaft slowly enough so the person watching the indicator can track what is happening to the needle until it gets to the bottom position. When you get there, it's a good idea to write down what the measurement was on the bottom. Another point of frustration is that you might not be able to get to the bottom. When you try to rotate the bracket and indicator assembly to the bottom, a lube oil pipe or thermocouple or the base plate gets in the way. Don't worry. If that is the case, just rotate back up to the top and then rotate over to the other side and get the readings on the top and both sides. In a little bit, we'll talk about the validity rule, which will help you figure out how to determine what the bottom reading would have been even if you couldn't have gotten there. Just like you did in the last rotation, verify what the indicator reading was on the bottom and then rotate the shaft slowly enough so you can watch what is happening to the needle until it gets to the side position. When it gets there, remember to write down what that measurement was on your recording sheet. Return back to the top position and observe what the indicator reading was. Hopefully, it returned back to 0. It is not unusual for the needle to be pointing close to 0 but not exactly at 0, perhaps somewhere between a -2 and a +2. If it is slightly off, re-zero the indicator and capture another complete set of measurements to check for repeatability in your readings. I'd like to stress the importance of getting good measurements here. Everything we do pivots on the accuracy of these measurements. I also believe that one of the major problems with aligning rotating machinery can be traced back to this particular step. It is my observation that many people do not know how to read a dial indicator correctly, principally because no one taught them how to do it. The key to getting good measurements is to take your time, double-check your measurements, and write down the readings correctly on your recording sheet. It is easy to get the top and bottom readings right, but it is very easy to write down the readings you got on either side incorrectly, like putting the measurements on the north side of the pump shaft on the south side of your reading circle. That, my friends, is a fatal error. What you got and where it was at on either side is just as important as what you got on the bottom or the top. In the tutorial that covered the preliminary tasks that you should check and, under certain circumstances, correct prior to aligning rotating machinery, we discussed runout. As you know, runout describes a condition where the shaft itself or objects attached to the shaft, such as a coupling hub, can be off-center or eccentric. We also discussed guidelines for acceptable amounts of runout, so there are going to be times where you have a couple of mils of runout that you're going to have to live with. Can runout have a detrimental effect when measuring the positions of the center lines of rotation? You bet it can. Here is a shaft with a coupling hub attached to the shaft. There is no perceptible amount of runout in the shaft or the coupling hub attached to the end of this shaft. The center line of rotation of the shaft is shown as a dashed line. The shaft on the right has a coupling hub attached to it that has a runout condition. In other words, it is off-center. The center line of rotation of the shaft is shown as a dashed line. The center line of the outer circumference of the coupling hub is shown as a dashed blue line. The high spot on the coupling hub is currently in the up position. Now, let's attach a bracket to the shaft on the left. Span across to the shaft on the right and place a dial indicator on the outer circumference of the coupling hub. Plunge the stem of the indicator in a little bit and zero the indicator. If we then rotate the shaft on the left with the bracket and indicator attached, when we sweep to the bottom, the indicator will still read 0, making it look like the shafts are aligned. But notice that the center lines of rotation of the two shafts are not in line with each other. Right now, the center line of rotation of the shaft on the left is aligned to the center of the coupling hub of the shaft on the right, but that coupling is off-center with respect to the shaft it is attached to. Understand that pure shaft alignment is the process of aligning center lines of rotation with each other. To override a runout condition, the dial indicator must consistently be at the same angular position on the coupling hub on the right when a measurement is taken. Let's do this one more time, but now let's rotate both shafts 180 degrees. Notice that the high spot on the coupling hub has now rotated to the bottom along with the indicator, pushing the stem of the indicator in, measuring the amount of misalignment, and showing that the center lines of rotation are not in line with each other. Once all the preliminary checks and corrections have been completed, the process of aligning the shafts can begin. When machinery is initially set onto the base, there can be a huge amount of misalignment between the shafts, and trying to use high-precision alignment tools may become an exercise in futility. Rather, some simple methods should be used just to get the shafts within the range of more accurate measurement sensors. Now, there is nothing wrong with using your eyesight aided with straight edges and feeler or taper gauges. Once the shafts are within 1/4 of an inch or so, you can begin by selecting one of the 5 basic alignment measurement methods. The face rim, reverse indicator, and double radial methods are used when the shaft-to-shaft distances are typically 20 inches or less. When the separation between the shafts is greater than that, it is advisable to use either the shaft-to-coupling spool or the face-face methods. No one tool or one method will work for every alignment challenge you might face. There are advantages and disadvantages for each, and there are separate training tutorials that will cover each one of these methods in depth. If you've never done any of them, then pick one and start understanding how it works. It may take a little time to become familiar with the first one, but with some practice and patience, you will eventually master it. Then, pick another one and work through it step by step. By the time you tackle the third one, you will probably begin to see a pattern emerge, and then the rest of the methods just keep getting easier and easier to learn. Measurement sensors like mechanical dial indicators, encoders, or photodiodes measure distance. They don't have any intelligence in them. A dial indicator is a great device to not only measure a runout condition, but it can also measure the position of a shaft center line. But it can't tell the difference between the two. Excessive runout occurs in about 5 to 10% of the machinery I've worked on, so it's not a prevalent problem, but you can't pretend that it's never there and that you have the only machinery in existence that doesn't have runout. If you measure for it and don't find it, then that's great. But if you don't check for it, and it does exist, it's going to possibly make you look foolish. The symptom of excessive runout is that it will produce vibration on the machinery. Imagine how you will feel if you just got done aligning a drive system, started up, and it's vibrating more than it did before you aligned it. If you measured it, told someone, and were instructed to align the drive system anyway, then you can act like a clairvoyant and explain that you can override the runout condition, align the center lines of rotation, but the machines are going to vibrate once you start it up. At least then, you won't be the one who looks like the fool. Hey, thanks for your interest in shaft alignment. I know how busy you are, and I appreciate the time you took to watch this presentation. I hope that you learned something that's going to help you perform your work better and provided you with a clearer understanding of what it is you're supposed to be doing. After 37 years of working with rotating machinery in a wide variety of industries, I've gained a great appreciation for the degree of difficulty that comes with the responsibility of installing and solving problems with this expensive and complex equipment. Alignment is not easy to learn, and it's much more difficult to master. To me, a true professional knows all the different alignment methods, understands the limitations of the tooling that they're using, and has the ambition to want to learn more every day. The vast majority of what I hope is useful knowledge came from working with talented people like you. So if some of the information in these training tutorials are not perfectly clear, or I've made a couple of mistakes, let me know, because I want to try to get this information as clear as possible to everybody. Well, best of luck in all your endeavors, and I've got to get back to work.